Firstly, big thank you to joining and going to be talking today about a big topic, two letters. Who knew that two letters can cause such a headache for a lot of us in this industry? But certainly AI is coming for us, and it feels a bit like a tsunami of compute, and as an industry, this is definitely impacting the way that we're designing data centers. So really an interesting topic and something that we're talking to a lot of our customers about here at Cadence. So today's agenda, I will just checking why that's not adjusting on the screen. There we go. There we go. So today's agenda, firstly talking about the AI challenge, and why it's causing us such a big challenge at data center design scale, and then actually kind of flipping it on its head and talking a little bit about how AI can also be part of the solution to this challenge, and how we can leverage AI in building and optimizing our data centers moving forward. And that kind of leads nicely into digital twins and digital twin technology, and how they are proving really vital in this challenge of AI compute, and hopefully some time at the end for some Q&A. So before we dive into all of that, a little bit on who Cadence are. So I've been around in the data center space for about 3 years, so fairly new to data centers. So I thought I'd just explain a little bit about who Cadence were and why on earth we're talking to you about data centers. So really, Cadence have been a sort of pivotal leader in simulation space, and they've been doing that for around 30 years, more on the electronics design at EDA and IP levels. But if you think about any of the compute and any of the hardware that's sitting in your data centers, the chances are that the Cadence simulation and computational software has been involved in the design of those along the way, right down from the sort of individual chips and component level, right up until the sort of system design. And they layer on top of that a sort of AI platform, and that helps our computational software understand the physical behavior of different systems, and allow us to create these digital twins of all these different verticals that you can see kind of running along the top, and one of them being data centers. So we've got a long history of understanding the performance of these systems, and now with the kind of the pressure coming from AI, we can see the kind of importance of understanding these systems and being able to optimize them moving forward. So that's kind of where Cadence sit in the landscape. I also will be using some of the statistics and data from our own research that we did around sort of 400 IT facility and business leaders globally, working in global data centers and data center organizations. So I've got some of the sort of the main stats sort of throughout today's session. But if you want to read more, grab your phones, grab the QR code, and you can download the ebook from the Cadence website if you want to know a little bit more about the challenges. And it's not just around AI. This is really around innovation and how those organizations are dealing with the challenges of technology, solutions for those challenges, and yeah, a lot of really interesting sort of statistics in there. So do go and download your copy there. Okay, so let's get into it. As I mentioned, AI is coming for us. It's definitely here, and even in the language we're using around what is a data center, data centers kind of being rebranded as AI factories, just a factory that's creating tokens to do AI compute. So even in the language we're hearing within the data center space is sort of tailoring towards the fact that AI, there's an inflection on AI, and there's sort of three main areas as we see demands on the industry coming. Now, the first one is just from a pure resourcing perspective. We've been having conversations around 120 kilowatts for a rack. How do we safely house those in our data centers? And then the GTC in March, NVIDIA launched or told us about their roadmap for 2027, that they expect their racks to be around 600 kW per rack. So, significant power density rises coming for us and here. And that is a challenge in way of how do we safely house these within existing data centers, or do we just plan for future deployments? And we've heard kind of planning around, if you're looking at 2030, you should be sort of planning for, if you want to use these AI high-end AI GPU compute, you should be looking at kind of a megawatt per rack. So, it just sounds sort of ludicrous, really, but it is coming, and these are the kind of rack densities that we're going to have to deal with. But it's not just about power. I've also sort of put a stat from a sort of a typical hyperscaler data center that might use anywhere from 1 to 5 million gallons of water a day. And as water, especially when you're competing with kind of local projects for housing, water use is becoming scrutinized more and more. So definitely a big resource demand challenge for us to tackle. And at the same time, capacity demands. So even though we're building data centers at record pace, the amount of available power and available data center space is actually going the other way and continually drops. So in certain markets, the vacancy rate's kind of under 2%. So you really haven't got an awful lot of choice in terms of getting a capacity. So you might look at what's being built, and then the story isn't much better, I'm afraid, that there are some areas where pre-leasing of data centers that are mid-construction is up in the 90s. So you can't even really get your name on a site that's being built because it's probably been taken, and this is all driving increased costs for renting, and so people are starting to say, well, it's getting harder for us to build, definitely harder for us to lease. We should probably take a look at our own infrastructure in-house, and maybe we can do a better job of using our own capacity. And that's great news, because statistically, the number that we see for people kind of leveraging of their own in-house capacity is fairly low. We're seeing kind of that when you get to the 60% of your design capacity, you start to get into difficulties in terms of leveraging that last 40%, and an average number is around 40% stranded capacity. So you're not actually able to use it because you've run out of one of your resources, and that can typically be like a cooling problem, like you might have hotspots that you can no longer deploy. It might be a space problem that you've run out of physical space or use space, or power phase balance. There's lots of reasons, because you're trying to balance all of these different resources, and you usually run out of one of them before the others, and that causes problems. So even using your own in-house capacity can be a real challenge. And then we also know that legislation is coming for this industry in Europe and America particularly. There's more legislation in terms of resource and reporting your resource utilizations. And we've seen governments in the past putting in those moratoriums to say, actually, we're not going to be building any more data centers because we've run out of power, or there's a drive for being more efficient. So, there's definitely these three areas that we see coming for us in terms of demands on the data center space. Now, when we look at the key AI loads and the impact on the power grid, so from a power perspective, we've already talked about this high power density, and certainly if you're trying to manage 600 kW per rack, this is going to be an impact on the grid. But it isn't just about this the high number. It's also the profile of power within AI compute, and we see these rapid fluctuations from idle power to way over the design load, 50% in some cases over its thermal design load, in these millisecond spikes that could take a rack from a few kilowatts up to this 600 kilowatt, or currently 120 kilowatts for a full rack. So how you sort of deal with that from a provision perspective is very challenging. And then it's also it's very unlike traditional workloads in that we don't have this intermittent usage. We have this continuous process or continuous load requirement for the training and in the inferencing. But even between training and inferencing, those two have very different profiles. And actually, one of the hardest things to manage is when there's a pause in activity and you ramp down the other way almost instantaneously from 120 kW per rack down to a few kilowatts, and your system has been charged, ready to deliver this high load, and instantaneously have to dissipate through the system safely. And so we're seeing a lot of challenges around how we kind of set up for powering this compute. There's also really large levels of data management, or data movement between the different nodes within the compute. So generally AI will run across multiple GPU nodes, and you're transferring a lot of data between those nodes. And so this is creating significant network traffic, and this is impacting power consumption even further. So we're really at this challenge of how do we deal with the scalability challenge for AI. The power demands are getting rapidly increasing as the models become more complex, and this really requires data center infrastructure to be really flexible and adaptable, but managing these high densities and these high fluctuations. So if we move from the grid down into the data center, we kind of see a few of the same problems. So we've already talked about power draw and the fluctuations that we need to manage, but with power comes the cooling requirement that we need to handle for that. So not only do we need to bring cooling of such levels and such density to small spaces, they also need to be much more rapid in terms of their control. So a traditional air cooling system, there may be a delay of 5-10 minutes before a chilled water valve opens and the cold air reaches the space that you need it. Well, you won't be able to wait 10-15 minutes if your GPU ramps up instantaneously, and you need to have the cooling respond to that almost immediately as well. There's definitely a need for specialized UPS systems. So you can see vendors are coming to the market with sort of AI ready power delivery, and that's certainly something that we see both on the UPS and the power distribution systems, and also true of rack design. So rack design now needs to consider these extreme power densities and the cooling, bringing the cooling, we're talking about liquid cooling here, being able to provision that at the rack level. So the rack design is also important when thinking about leveraging AI. So talking about the liquid cooling, this is something that's definitely coming for us. We've, as an industry, we've sort of dragged our heels with liquid cooling and said it's going to be coming. It's going to be coming for years. We've been saying that sort of same story, but now it's certainly true from the sort of research we had. We said almost half now are actually using liquid cooling. We get asked quite often, is there a flavor that we see going to be more prevalent, whether it's the sort of cold plate cooling or immersion? And you can sort of see from the numbers, they're fairly even, and I think there's really use cases for both. So I don't see it really as a one or the other being more prevalent. I think it just depends on the application and the type of design that you're trying to implement. But certainly liquid cooling is coming for us and being used. But there's still these feelings around liquid cooling that we have. We're a very risk averse industry, and so you can see, still quite high numbers, 40% think that they feel that they're nervous about introducing liquid cooling into their organizations, data centers. Almost 60% saying they're really keen to use it, but find implementing and managing the challenges a bit off-putting. And so we see people kind of making that decision about, do we bring it in-house and try and retrofit, or do we go outside to specialized facilities that are being designed and built to use liquid cooling for this AI compute rather than bringing it in-house? And you can see, the 26% at the bottom sort of showcases that there are certainly organizations or data centers out there that won't be using liquid cooling and don't have plans to, because the cost maybe is impacting thinking about bringing it in-house. So, or they haven't got the expertise maybe to be managing liquid cooling, and so they just will outsource that problem. So what we're noticing more and more is that that there are solutions or complete solutions to this AI problem, in that this is an example of an NVIDIA SuperPod where they take care of the rack design, the cabling design, the compute, and then they will give recommendations for partners if they don't, if they don't build the cooling system or the power systems themselves. They will have a list of sort of agreed vendors that can provide suitable levels of cooling and power. So you can kind of take a complete solution from one of these vendors so we're seeing definitely the industry moving away from deploying those individual servers into racks. There is still a little bit of that, but when you're talking about doing kind of AI, big AI compute solutions, there are definitely opportunities to just leverage an entire system from one of the vendors, and that takes care of a lot of the design questions, and then really it's around how you can operate that in the facility. So I thought it was interesting to just flip it on its head a little bit, because yes, so certainly AI is coming and causing us a lot of problems in terms of how do we house this extreme level of power. But interestingly, AI could also kind of come to the rescue a little bit and help us design and optimize our data centers for the future. Now, I mean, AI has been around for a long time, and certainly in data centers, I think this is a paper from 2016 where Google used DeepMind AI to reduce their cooling bills. So looking at their cooling control strategy, using AI to look at a lot of the telemetry and understand where they could make adjustments to the cooling system to save on energy. And that's kind of a very typical use case for AI. But we went ahead and asked our kind of audience of where they've been using AI in data centers, and a high number use it sort of for fault detection. So, looking at those trends, looking at telemetry data and looking for faults. A high number of natural language assistants and being able to just talk and ask questions. Looking at forecasting and automating a lot of the capacity management is a good use case. We know within the data center space we are struggling for labor resourcing and skilled labor, and so AI is a kind of a good use case for filling those gaps, allowing the trained people that we do have to do more in less time. And so that's where we see a lot of the AI applications coming in. And then lastly, kind of advising on energy management. So lots of tools out there are building AI in probably adding to the problem a little bit, because the tools themselves have to run somewhere. But I think as a vertical and as a industry, we've got to look to use AI, leverage AI to help us design and optimize and build the best data centers that we can. So this leads really nicely into the next topic of digital twins. And I just wanted to talk a little bit about how we see here at Cadence digital twin technology helping us manage this wave of compute that's coming from AI, and talk a little bit about how the solutions and digital twins can kind of help us move forward. So maybe start with what a digital twin is, or data center digital twin, and really think of it as just this virtual replica of a physical data center. And it can really combine all of your physical design information. So it feels like a single pane of glass where we can look at IT systems in their rack locations. We can look at the cooling system components, whether this is air or liquid, your power distribution, the networking. All of these components can be pulled into a digital replica. And that then allows you to look at your current performance, but also look a little bit into what's going on in the future. What's key about digital twins is they're connected to their physical counterparts. So it's aware of those changes that happen in reality, and will update with those changes automatically. And then the kind of final component of the digital twin is that it has this capability of understanding performance from understanding physics, because of doing simulation and using AI. So because it understands the physics of the system, it's able to understand why it's performing in a certain way, and that can then help you understand where you have problems. But we talked about this forecasting, being able to look into the future and say, well, what if I change something? What if I bring in one of these super pods? What if I go to do liquid cooling? What does it look like in my data center? And before I implement it for real, let's try it out in the digital twin and see what the performance looks like. So that's really what the value is of a data center digital twin. But what's also key about it is that it spans the entire data center life cycle. So I'm going to take you through that and show you kind of how the physical and the digital evolve together over time. So we see these three main stages that we're going to talk about: design, commissioning, and operation. Firstly, the digital twin is built, and that helps you design and optimize the data center. We can ingest all sorts of design data from CAD and from BIM, and then that allows you to predict performance and virtually prototype the optimization of your data center. Once we're happy, the data center is constructed, and at this point, the design is complete, the facility is built, and we look at commissioning. So the design team will come, you quite often survey, make sure that the physical data center is behaving. You'll do some testing, some IST testing, and at the same time, the digital twin can be connected. They can pull all of that that data from the tests, and make sure that the model also reflects reality. We then can pass the digital twin over, and as the data center is then commissioned and brought online, we can connect the digital twin through the live monitoring and any workflow systems, and it now will be responding and reflecting exactly reality. And at this point, you can then use it operationally. So we can start to ingest change requests, and these change requests could be coming from any tools that the organization have in place, whether it's a ServiceNow ticket, whether it's a DSIM asset change, whether it's somebody using a spreadsheet and they just like updating the spreadsheet. That can all be ingested into our digital twin. We can predict performance of those changes, and again, help to optimize the performance. And then those are pushed back and finally implemented in the physical twin, and that makes sure that your performance is maintained. And at some point, you might then return to a big design change. If you're thinking about, in this case, let's think about liquid cooling, you might then go and do a big design change for major upgrades. So we went out and talked about kind of how people are using digital twins, and you can see quite a lot of using it for network planning management, space planning management, optimizing capacity, managing and introducing AI, and introducing and managing liquid cooling. So digital twin use is definitely up and being used in helping with this challenge of AI. So here at Cadence, we offer the Reality DC digital twin platform, and this really will allow you to optimize the data center from design and operation standpoint. It can tackle the air and liquid cooling solution, so it's a multi-physics solution. It also operates at multi-scale, so we can actually evaluate the performance from the chip all the way through to the campus. So if you have multiple data halls that are all sharing the same chilled water infrastructure or sharing the same power distribution system, or you want to think about the data connectivity from a switch in room A to switch in room B, the Reality DC digital twin platform can simulate that entire system all the way up to the campus. And as the scale of the problem gets bigger, we've had to move across to doing GPU accelerated performance. So that allows us to simulate these systems in really very, very quick turnarounds, almost 60 times the speed that we were doing on traditional CPUs. So when you hear of people saying, well, simulation generally takes days or weeks to get an answer, that's some outdated information, because in terms of GPUs, we can get those answers out in minutes now. It really is an incredible change in the way that compute can be optimized using GPUs. Then we talked about the life cycle. So, we can basically help design all the way through to operations to accelerate your planning and deployment. And once it's an up and running data center, we can connect it to live telemetry and connectivity so that the digital twin is automatically updated with any changes that you make. And we've also put in our own AI infrastructure, which I'll talk a little bit about later on. It comes with a ecosystem of components. So there's about 20,000 components now. At Cadence, we're very much vendor neutral. So we have components for all sorts of vendors, all the way from the individual IT assets to the racks, to the power systems, to the cooling systems, outside into the chiller yard, the generators. And that allows you for very quick drag and drop of those items. And they, what's good about it is that you don't have to build anything yourself. They are basically accurate replicas of the physical counterparts, and they're also validated by the manufacturers. And once your data center is live, then these components can be updated from your real-time monitoring to reflect any of those operational changes. And very quickly, just talking about AI, we are also embedding AI into the platform in various guises. On the left side, I won't talk about all of them, but the three that I think are kind of key are talking about performance. So AI we can use to identify issues within the data center and offer recommendations. We can try those recommendations and simulate them in the digital twin to say, well, what does it look like if you made these changes? And they might be simple changes like a hotspot and there's a tile missing, or dampers closed, or there's blanking plates that are missing, to more sophisticated types of change like a cooling system optimization or control system change. And through all of that, we have built our own chat, so you can ask lots of questions in natural language, really interesting questions like, where's the best place to put 100 kilowatts of load? Or what's my phase balance on the PDUs, and where should I put this load to try and improve my phase balance? To how do I optimize my cooling systems to save on PUE? And, so lots of really good questions that you can use natural language to, and then the system can respond. Now, I talked a little bit about NVIDIA offering this kind of solution. They also talked at GTC about the fact that if you're building a data center or designing a data center, you should be building a digital twin first to leverage all of the good stuff that we've talked about. And they actually NVIDIA announced an Omniverse blueprint for AI factory digital twins, and really proud that Cadence was kind of part of this partnership, so that you can design the next generation of data center using Cadence tools to simulate how these will perform and optimize them through our technology. And we at the same time launched at GTC our Cadence Reality Omniverse experience, where we are leveraging the Omniverse using the underlying technology is OpenUSD, but leveraging that to give you, and I'm not sure how crisply this is coming across on the stream, but it really is a real high fidelity digital twin model. So it looks and feels exactly like reality. It has all of the components that you can imagine from your BIM models. And so when you're working in these different siloed design teams, you can bring all of the data together in the Omniverse digital twin. You can simulate it, which we're showing here, and visualize the impact of all of those different changes from those different teams in one place. So yeah, but really big project for us, and we're really happy to be launching that together with NVIDIA. Okay, well, it's gone. 30 minutes have flown by, so I will leave you just with a couple of conclusions. I really hope today was useful for you and you found this interesting topic. Certainly from our side, we're seeing that AI is transforming every layer of data center design, from power and cooling, from weight on the floor, space, data network connectivity. And so this is really a big challenge for the industry. But we can also see that AI could help us be the solution to the problem, and help us design and optimize the most performant data centers of the future. And with that link into digital twins being really an essential tool for simulating, testing, and optimizing the next generation of data centers, whether you're designing for AI or you've got an existing site and you're trying to bring it in and you have questions around how it will perform, then digital twins are really the way to test that out before you implement. If you want to know any more, that's my email address, or you can come and find us on cadence.com. But with that, I'll say thank you very much. And if there are any questions, happy to stick around and answer them.
Amazing. Thank you for that so much, Mark. We do actually have a question from James Lawson in the audience, which is, what is the level of detail in Cadence's digital twin?
Oh, great question. So the software has been set up to be able to import information from lots and lots of different areas and spaces. So we can connect to BIM and pull in all of that great information. And in terms of things that we need, would be assets on the floor, racks, IT, your cooling systems, the control algorithms that you're interested in. But again, because of the vendor libraries we have, all of that information and the behavior of those components is already handled by the package. In terms of how sophisticated the models can go, we can do the kind of full one-line diagram for power. So we can do the full connectivity from your IT assets through to the rack-mounted PDUs, RPPs, PDUs, UPSs. And then you can also, what's great about it is you can fail any of those components too and see what happens if you lost power to a panel, or if you lost some cooling to your pumps. What does the data center look like over time, and how long have I got before some of my critical applications kind of overheat or run out of power themselves? So lots of details. In fact, the amount of data that we consume is all kind of automated, so it doesn't mean that the model build takes longer and longer. In fact, we can just automate a lot of that stuff. So yeah, power networks are there. We can also model the chilled water infrastructure. So if you're looking at water delivery or coolant delivery to CDUs, that can all be handled within the digital twin. So yeah, we can really go as detailed as you like. So yeah.
Excellent. Hopefully that answers James's question. I also, you touched on it there, want to know, how do the digital twins deal with failure scenarios?
Yeah, so they can both handle sort of what we call snapshot simulations, but also time-based simulations. So a lot of the failure stuff we do is around how does the system perform when something goes wrong over time. So if we talk about a cooling failure, you might, let's say you've decided that the chillers will fail, but you keep your pumps on UPS, and those pumps will be pushing cold water around the system, and maybe you've got a buffer tank that's in place that has a certain amount of storage. So that would be a nice scenario that you'd want to fail and see how long that chilled water stays going around the loop, and eventually the water will increase in temperature, and eventually your data center will start to heat up. So people want to ask those kind of questions. How big do my buffer tank need to be to give me 10 minutes to run down and turn the generators on, or do I even need a buffer tank? Can I get away with just the amount of water that's sitting in the loop? So there's those kind of questions around the cooling side. And then on the power side, people are really interested in if I'm overloading any of my critical infrastructure from a power side. And for that, you have to think a bit about your redundancy plan. So generally you have this sort of A and B concept if you're running sort of a two-end system, and you may be looking like at your power loads being pretty good, but actually if you lost supply A, everything comes across to supply B, and supply B needs to be sized accordingly all the way up the chain. So the digital twins here at Cadence allow you to automatically fail every component in the system, and it will then give you a report to say, if you lost this component, then these are the components that will run out or have loss of power. So it can give you all of those single points of failure in a really complex power systems, which I think is actually an incredible value. And then you layer on top of that the future, that sort of any plan that's coming in, you need to understand the implications on the power side and the cooling side. So not only do you plan for everything working, you should really be planning for what's a worst case failure to make sure that you're covered.
Yeah, it seems that Heathrow probably should have used the digital twin to make sure that their systems are a bit more robust.
Yeah, exactly.
Their recent power outage. We have just added an influx of questions. One says, how can digital twins help with the transition from current rack power density to 600 kilowatts per rack?
Yeah, it's a great question. So I think that's exactly what the conversations that we're having with a lot of people. They're coming our way and going, we have a 5 to 10 kilowatt design limit on each of the racks. So the first thing is building a digital twin unveils that performance that you can get. So you can literally drag a 600 kilowatt system into the digital twin, solve that, and it will tell you how it perform. And it may be that you're lucky that you've got enough redundancy and availability in your current site that it will survive. And your engineering teams can rally around that and go, okay, look, how do we make that safe? So what extra systems do we need to bring in place? Maybe we need cold oil containment, maybe we need liquid cooling, all of these what if. So if you think of the digital twin as your what if playground, you can try out all of these things safely in a digital space rather than trying it out in the real thing. So that's the first thing I'd say, is once you have built a digital twin of your space, you really are free to try anything and everything from all the vendors that are trying to sell you their goodies. You can just plug them in and see how they perform. Yeah.
It's almost like a simulation video game, essentially.
Exactly.
If anyone's played like Planet Coaster or SimCity or anything like that, it's sort of like that, but with a data center, I guess.
You're right, and the fact that, so we did something in the Omniverse the Omniverse, what that gives you is such lifelike representation that it feels like it's there. And at GTC, I did a sort of experience with at the Apple Vision Pro, where you're basically in. The experience is that you're there and you can touch it and feel it and move it and press it, but you're just in an empty room. But it is becoming the way that we can see future interactions with these data centers, especially edge ones where you may not have staff, being almost a sort of virtual reality computer game, like you say, but fully connected. So it's responsive and it's behaving as if you're in the real space. Yeah.
Amazing. And there is one last question from Carl Turbot, who says, is it feasible for the digital twin to monitor the harmonic distortion generated on the system?
So we don't currently do harmonics. That's a good question. So I think that's one of the areas that we don't currently cover. Yeah.
Okay. Perfect. Right. I'm going to let you go, Mark. Thank you so much for that session. It was really informative. And yeah, it's always interesting to see how we can use AI to enable AI. So thank you so much.
No problem. Thanks very much, everyone.